suppose that I'd like to determine the value of this integral. All right, I'm going to call this integral from epsilon to r, I of alpha phi epsilon r. And I'll be interested in the value of this as epsilon tends to 0 and r tends to infinity. I'm going to view this as a keyhole contour. So I'll go from epsilon to r, and that will be my capital I. I'll go all the way around the circle. I'll come back in and then back around the circle. I have a branch point at 0 by virtue of the non-integer power on x, and the branch cut will be taken to go out along the positive real axis. Okay? I'll have problem points wherever the denominator is 0. Okay? I'm going to complete the square because that will be an effective way to treat this denominator. This is going to be x plus cosine phi squared, right? And then I had a plus 1, and I didn't have a plus cosine squared phi. So I'm going to have to add 1 minus cosine squared phi, or x plus cosine phi squared plus sine squared phi. All right? So I'm going to have problem points at negative cosine phi plus or minus I sine phi. Okay?
Can you do that again?
Sure. I'll have problem points at negative cosine phi plus or minus I sine phi. That's because I have problem points where this equals 0. All right? They'll be simple poles. Negative cosine phi plus or minus I sine phi. That's equal to e to the I pi plus or minus phi. Convenient. Okay? E to the I pi plus or minus phi. So I'm going to have a problem here and a problem there where this angle is phi. Does that make sense to everybody? All right. All right, great. So my loop integral will equal I, so that's along that top part, plus an integral from 0 to 2 pi. It'll be r e to the I t to the alpha I r e to the I t dt divided by 1 plus 2 r e to the I t cosine phi plus r squared e to the 2 I t. That's the loop at infinity. As I go along the bottom, z will be x e to the 2 pi I. I'm going along the bottom from R to epsilon. So that means I'm going to subtract. It'll be x e to the 2 pi I to the alpha e to the 2 pi I dx divided by, since e to the 2 pi I is 1, the denominator is just going to be exactly the same as it is in I. Just like that. And then, of course, I'll have the little itty bitty baby integral 0 to 2 pi, and it'll be epsilon e to the it to the alpha I epsilon e to the it divided by 1 plus 2 epsilon e to the it cosine phi plus epsilon squared e to the 2it. Now I'm going to want to be interested in this integral when epsilon goes to 0 and r tends to infinity. So I'll have I minus e to the 2 pi I alpha I. Plus, all right, what happens up in here? I've got r to the alpha plus 1 divided by r squared. As r tends to infinity, these two terms pale in comparison. So I'll have r to the alpha plus 1 minus 2. So I'm going to write that as order of r to the alpha minus 1. Okay? Just because I don't want to write it all out. Here, it's going to be epsilon to the alpha plus 1 divided by epsilon's going to 0. So those two terms don't matter. All right, so this is going to be order of epsilon to the alpha plus 1. If I want these two contributions to tend to 0, then I need alpha plus 1 to be greater than 0 and alpha minus 1 to be less than 0. So -1 less than alpha less than 1. All right? All right, if that's true, these two are gone, and I can simplify this business immensely. I'll have e to the I pi alpha, e to the minus I pi alpha, minus e to the I pi alpha, capital I. So that gives me e to the I pi alpha times -2i sine pi alpha times capital I. All right? All right, so that's one part of the manipulation. In order for us to determine the value of capital I now have to do this loop integral by Cauchy. That requires space, so I'm going to get rid of all this business. All right. All right, so now we're doing the loop integral by Cauchy. So it will be 2 pi I times the sum of the residues. All right, let's do the residue at e to the I pi plus phi. Okay? So what will it be? Once again, I'll use L'Hopital. Okay? So I'll have e to the I pi plus phi to the alpha divided by 2 cosine phi plus 2z. All right. And so what is that going to be? Well, that's going to be 2 cosine phi minus 2 e to the I phi. All right. So that's minus 2i sine phi. Okay. Then we're going to have the contribution from e to the I pi minus phi. E to the I pi minus phi to the alpha divided by, now it's just going to be pi minus phi. Okay? So it's going to be minus 2 e to the minus I phi. Which is 2i sine phi. Okay? At this point, the 2i cancels out neatly, and we'll have pi over sine phi e to the I pi alpha and then let's see what's left up in here. E to the minus I phi alpha minus e to the plus I phi alpha. So this gives me pi e to the I pi alpha divided by sine phi times minus 2i sine alpha phi. All right, these two things are equal to each other. So the minus 2i cancels out. Importantly, the e to the I pi alpha cancels out. And so we end up with our integral given by pi over sine phi divided by sine pi alpha. Pi over sine phi, sine alpha phi divided by sine pi alpha. And that should be what we're asked to show.